Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for week number 9 for wireless and mobile communication. We are continuing the discussion from our previous lecture regarding the modulation techniques for mobile radios. We started discussion on digital modulation, and we discussed that modern day cellular communication systems are using digital modulation techniques because of the various advantages that we get from the digital communication in terms of better performance and cost effectiveness for digital systems. We have further advantages of having different signal processing schemes easily implemented in digital communication systems. Although these advantages come with a price of having a higher bandwidth, because the digital system require relatively larger bandwidth as compared to the analog communication systems. So we continue our discussion on digital modulation technique. In order to complete the discussion, we first start our discussion on digital pulse modulation, that means the baseband modulation. Pulse modulation means representing the digital information by using pulses. These pulses are actually low frequency pulses which represents only baseband signal, and that can be transmitted through a baseband channel, for example a copper wire or coaxial cables. This pulse modulation can be made in binary coding, where you have two different waveforms to represent data bit 1 and data bit 0. So data bit 1 would be represented by one type of waveform or one type of pulse, and data bit 0 would be represented by another type of pulse. In that case, the data rate would be equal to the bit rate, and the symbol rate is also the same. Sometimes we combine different bits into a symbol, and we create waveforms relevant to those symbols. We call that M array coding, where M there are a total M symbols are represented by waveforms. For example, if we combine two bits together, so that becomes a 4 array system. 2 raised to power 2 is equal to 4. So we have a 4 array system where M is equal to 4, and we are combining two bits, which is represented by K here. So 0 0 would be represented by one type of waveform, 0 1 would be represented by another type of waveform, 1 0 would be represented by a third type of waveform, and 1 1 would be represented by a different type of waveform. It should be waveform number 4. Sorry for mistake. I will correct in final version. So symbol rate would be equal to the bit rate divided by K. So in order to transmit a number of bits, actually we need to transmit lesser number of symbols, because when we transmit one symbol, we actually transmit two bits at a time. So this is the relationship which exists between symbol rate and bit rate. We use different modulation technique, baseband modulation techniques relative to baseband communication. We call them binary line codes, although there are numerous line codes which are used in practice, but here I am presenting only a few just as an example for line codes. First type of line code is unipolar NRZ. NRZ stands for non-return to zero. For NRZ codes, the symbol, waveform or pulse exists for entire bit duration. So these dotted lines, they represent actually a bit duration. So the waveform exists for entire bit duration. For unipolar NRZ, we use a specific amplitude to represent binary 1, and we use 0 amplitude or no pulse to represent binary 0. So zeros and 1, they are represented by presence or absence of pulses. Similarly, we use another type of code which is called polar NRZ, where we use two different amplitude levels. Binary 1 is represented by an amplitude level, say for example A, and binary 0 would be represented by the negative pulse with an amplitude minus A. So polar pulse scheme is represented by having positive and negative pulses. Similarly, we have another scheme which is known as RZ, or return to zero. These pulses exist only for half of the bit duration. So the width of the pulse is actually half of entire bit duration. If we have unipolar NRZ, in that case, similar to the unipolar NRZ, unipolar RZ has pulses for binary 1, and there is no pulse to represent binary 0. So binary 0 is represented by no pulse, like here, and 1 is represented by a presence of pulse, which is actually half of bit duration wide. Similarly, if we have bipolar RZ, in that case we use positive and negative pulses to represent different symbols. Sometimes we call it RZAMI, or alternate mark inversion. RZAMI. AMI stands for alternate mark inversion. Alternate mark inversion means we use pulses to represent binary 1 and no pulse to represent binary 0, but the pulses are used in a way that consecutive pulses have opposite amplitudes. For example, 1 is represented by a positive pulse, the negative 1 would be represented by a negative pulse. Similarly, the 0 would be represented by no pulse, the next one would be represented by a positive pulse because the previous pulse was negative, and then zeros are represented by no pulses, and then next one is represented by a negative pulse. We have another coding scheme which is named as Manchester coding or Manchester NRZ. In that case, the information is represented by a transition of pulse at half of bit duration. For 1, we see a transition from positive to negative. For 0, we see a transition from negative to positive. For example, binary 1 is represented by a positive pulse at the beginning. At half of bit duration, it goes to the negative side, and the remaining half is at a negative pulse. Similarly, the next one is also represented by a positive pulse, which goes to the negative side at half of the bit duration, and then the rest of the half pulse is negative. Similarly, for binary 0, the start of the pulse is negative, and we see a transition from negative to positive here, and then the rest of the half is the positive pulse. So basically, information is represented by how the pulse transition from one side to other. For binary 1, the pulse transition is from positive to negative side, and for binary 0, the pulse transition is from negative to positive side. As I mentioned, these are only few examples of binary line codes. There are other codes as well, which I am not going to discuss here, but these certain codes, they have certain advantages. For example, in comparison to NRZ and RZ, the RZ has better synchronization capabilities and as compared to NRZ, but NRZ has better bandwidth efficiency as compared to the RZ pulse. So these pulses have contradictory properties, so we choose the type of line codes which are more appropriate for our system which we want to design. So we now discuss the M-array coding. As I mentioned, for MRZ signaling, we combine some number of bits to make a symbol. This M-array signaling has certain advantages. However, there are some compromises as well in MRZ coding. This M-array coding. First of all, the main advantage is we have a relatively lower transmission rate as compared to the binary coding, because the symbol rate is actually bit rate divided by k. So if we transmit one symbol, In that case we transmit actually k bits, so a number of bits are transmitted simultaneously. Therefore this M array signaling reduces the required bandwidth for transmission. However, because of the multiple signaling present in the system, so we have generally low signal to noise ratio because there are multiple amplitudes of pulses available, and these multiple amplitudes, they result in relatively higher bit error rate. So error rate is relatively higher as compared to the binary signaling. So for M array signaling, we we make a group of bits, we combine those bits to make a group and transmit that group simultaneously. So one pulse is represented by a symbol. So bit rate which is given as RB, it gives you a transmit bandwidth of RB by 2. But whenever we go to the M array signaling, in that case symbol rate is smaller than the bit rate. So RS is actually, it should be RB by K. So minimum symbol rate will be RS by 2, which is RB by 2. That means the required bandwidth goes down by a factor of K. So the group that we make, it reduces the required bandwidth for transmission. However, we have a trade-off here, that this will give you a higher bit error rate as well. So we get an improvement in the bandwidth at the cost of higher bit error rate. This is an illustration of M array signaling. This is a digital pulse amplitude modulated signal. At the top you can see that we have used 8 possible amplitudes, starting from 0 to amplitude number 7. So there are 8 possible amplitudes, and we are using 8 amplitudes to represent a symbol. You can see that 8 is actually 2 raised to power 3. Therefore this 8 array system is actually representing a 3-bit symbol. So each pulse here is represented by 3 bits. For example, below is the binary pulse code modulation equivalent representation. So 5, so if we have this bit pattern 101, which is equivalent to 5, so we will use an amplitude level of 5 to represent that particular symbol. Similarly, if we have 111 bit pattern, in that case these 3 pulses would have an equivalent amplitude of 7, so it will be represented by a pulse that have an amplitude level of 7, and so on. So for M array signaling, we generally use a lot more amplitudes as compared to the binary symbols. So this was a brief review on the baseband signaling, which is pulse modulation. It is important to note that baseband pulse transmission is only possible for low pass channels. The signals that are going through a low pass system, you can take a low pass system as a copper wire or maybe coaxial cable, and a similar system, they are represented as a low pass channel. So this baseband pulse transmission can be used in this low pass systems only. Mobile radio channel or wireless channel is actually a band pass channel. So this baseband modulation is not used for the transmission over a band pass channel or mobile channel. At the back end, we may be able to use this baseband modulation in order to have communication between two base stations, or between base station and mobile switching center, because that may be a wired channel. But for the wireless transmission, we need to have a digital band pass modulation. So for digital band pass modulation, we need to translate the signal to the higher frequency, and in order to do that, we need to have a sinusoidal carrier so that we modulate the signal to the high frequency sinusoidal carrier in order to get propagation through the mobile radio channel. So for digital band pass modulation, so we have different waveforms, sinusoidal waveforms, which are used to represent different symbols, which then go which are then used for transmission over a mobile radio channel. Similar to the baseband systems, the band pass systems also has binary modulation schemes as well as multi-level modulation schemes, depending on how many bits are combined to form a symbol. This is a common example of band pass modulation schemes. So say for example we have this binary data, we are only representing the binary information here, 0 1 0 0. It is possible to represent the binary data using two amplitude levels. So say for example 0 is represented by 0 amplitude and 1 is represented by a specific amplitude of sinusoidal wave. So there are two different amplitude levels, and these levels represents the binary data. So this type of modulation scheme is known as amplitude shift keying or ASK. Similarly, we may use two different phases to represent the binary data. So we use one type of phase to represent binary 0 and another type of phase to represent binary 1. So these two different phases, they are used to represent two different informations, and this type of modulation scheme is named as phase shift keying, PSK. So basically symbols are represented by different phases. Similarly, we may be able to represent symbols by different frequencies. So we may have different frequencies which may be used to represent different symbols. So for 0 we use different frequency, for 1 we use another frequency, and so on. For different to represent different symbol we use different frequencies. So this type of modulation scheme is known as frequency shift keying. You can see that for all types of band pass modulation scheme, the carrier is a sinusoidal carrier, and we use the digital data to change one of the characteristics of sinusoidal carrier, either amplitude, phase or frequency, in order to have a modulated waveform. For digital systems, it is possible to change two of the waveforms simultaneously. Sometimes we use amplitude and phase simultaneously in order to represent the digital information. There are certain efficiencies associated with these digital modulation schemes. We generally interest in power efficiency and bandwidth efficiency of a modulation scheme. What is power efficiency? Power efficiency, represented by eta p, is the ability of modulation technique to preserve the quality of digital signal at a low power levels. Low power level, as we have previously discussed as well, we generally compare the power level with respect to the noise level. So the parameter that we commonly use is SNR for analog systems, but for digital system we commonly use another parameter, which is EB by N naught. This EB by N naught is actually representing the bit energy. EB is actually bit energy and N naught is the noise energy per bit. So because in digital system we generally work in terms of energies instead of power, so typically SNR is replaced by EB by N naught. So even if we have smaller EB value, so the modulation scheme should have a sufficiently good BER performance. So say for example, if we need to have a BER of, say for example, 10 raised to the minus 5, so we want to have this BER performance of 10 raised to the minus 5 with as low value of EB by N naught as possible, because having the lower value of EB by N naught would result in lesser use of power, so it will be a more efficient system. Generally there is a trade-off between this BER and EB by N naught. If we reduce this EB by N naught value, this BER value goes up. So we have to get a trade-off between these two in order to have an acceptable level of performance. Secondly, what is bandwidth efficiency? Bandwidth efficiency is the ability of modulation technique to accommodate the data in a limited bandwidth. We represent this bandwidth efficiency as data rate per bandwidth. So EB is represented as R over B, where R is actually data rate and B is the RF bandwidth. So how much data rate we can get out of a unit bandwidth. So any modulation scheme which can achieve higher data rate would perform better. Again, these two are contradictory requirements. We need to have a trade-off between data rate and occupied by bandwidth. As we try to increase the data rate, we generally require to have a larger bandwidth. So while designing a system, we need to have a trade-off between data rate as well as the bandwidth. Moreover, there is a trade-off between this bandwidth efficiency and power efficiency as well. If we try to improve the bandwidth efficiency, the power efficiency decreases. So again, there is a trade-off between bandwidth efficiency and power efficiency. So say for example, if we want to have a better data rate, higher data rate, in that case we would be required to waste more power into the system. Or if we want to preserve the power in order to save the battery life, we may need to sacrifice some of the data rate. So again, there is a contradictory requirement of having this bandwidth efficiency and power efficiency. So whenever we are designing a system, we need to make a trade-off and decide on an optimum value for a system design. I must mention that this bandwidth efficiency and power efficiency are not the only consideration in the system. There are many other factors that affect the system design, and those factors include complexity of the system, resistance to the mobile radio channel impairments, etc. So there are certain other factors as well which also affect the overall system design. So what is maximum bandwidth efficiency that we can get out of a channel? So that maximum bandwidth efficiency is represented by Shannon's theorem or Hartley-Shannon law, which represents the bandwidth which represents the capacity of the channel. It is a most famous result in communication theory, which says that the maximum channel capacity is B log to the base 2 of 1 plus SNR, and it can be represented in terms of this maximum possible value of bandwidth efficiency, which is channel capacity. This C is represented by channel capacity in bits per second, and this B is RF bandwidth, of course in hertz. So this C by B value represents the maximum bandwidth efficiency, and this is equal to log to the base 2 of 1 plus S over N. You must note that this channel capacity actually represents the actual or real data, not the retransmission or errors, because for error controlling we sometimes transmit the non-information bits as well. So those information bits are not included in the actual data rate. So even if so the maximum efficiency that we can achieve, it is dependent on signal to noise ratio as by N here, as is shown here. So if we increase the noise in any system, noise is higher, in that case this maximum bandwidth efficiency would be decreased. The same relationship is also represented by the maximum capacity. The maximum data rate that we can get out of the channel, which is named as the channel capacity, is represented by B log to the base 2 of 1 plus S by N. So this is the maximum possible value of data rate that can be achieved through a channel. You can see that this data rate is dependent, this capacity is dependent on the bandwidth, the B. If we increase the B, the data rate would increase. Also, this capacity is dependent on signal to noise ratio. So if we increase the signal power, it will increase the overall channel capacity as well, because having the higher power generally reduces the overall bit error rate for higher powers, and because higher energy signals, they are easier to be detected. So we get for large value of SNR, we can easily differentiate between different types of symbols. So detection, having easier detection, we generally accommodate more data bits onto the channel as compared to the lower SNR value. So increasing SNR also increases the overall channel capacity as well. You must note that this maximum value of bandwidth efficiency is the fundamental limit in the system, and we cannot get a data rate which exceeds the bandwidth efficiency than this value. Although people are trying to achieve this capacity, so people are trying to make different types of codes which are named as capacity approaching code, so that we can have the data rate which is very close to this maximum channel capacity. For most of the system, the achievable data rate is relatively smaller as compared to the channel capacity of the system. So with this we take up a couple of examples in order to calculate the overall channel capacity. So this is a first problem, which is actually example number 5.6 in our textbook. If the SNR of wireless communication link is 20 dB, so SNR is given as 20 dB. You should note that in this expression which is given here for channel Shannon's law, this S by N is not in decibels, this is a fractional value. So in order to use this expression, you should have S by N in a fractional form. So this 20 dB is transformed into non-decibel or fractional value, which is equal to 100. So we have a signal to noise ratio of 100 here. The RF bandwidth is mentioned as 30 kilohertz, so bandwidth is actually 30,000 hertz. So we want to determine the maximum theoretical data rate that can be transmitted through this channel. So maximum data rate is actually named as the channel capacity. So for this particular case, we are interested in calculating the overall channel capacity. So channel capacity is given by B log to the base 2 of 1 plus S by N. So if we substitute the value, so this is 30,000 log to the base 2 of 1 plus 100, and this comes out to be 199.75 kilobits per second. So the maximum theoretical data rate that can be achieved from this wireless link is actually 199.75 kbps. If we compare this data rate with US digital cellular standard, which were discussed in chapter number 1, in that case the data rate was achievable data rate was 48.6 kbps, and you can see that the actual data rate that was used in US digital cellular system was only 1/4 the theoretical possible limit of at the 20 dB SNR. Theoretical limit is this value, 199.75 kbps. Okay, let us take another example. So what is the theoretical maximum data rate that can be supported in a 200 kilohertz channel? So the channel bandwidth is given as 200 kilohertz for a SNR of 10 dB and 30 dB. So we have two different SNR values, 10 dB and 30 dB. So let us first solve for 10 dB. SNR of 10 dB means the non-decibel or fraction value is equal to 10. If we calculate the channel capacity or maximum possible data rate, that will be represented by Shannon's law, which is C is equal to B log to the base 2 of 1 plus S by N. If you substitute the values here, the bandwidth is 200 kilohertz and S by N is 10. If you substitute it here, you can see that the achievable the maximum possible data rate is 691.886 kbps. And if we try to compare it with the GSM standard that was discussed in our first chapter, you can refer back to the first chapter. The GSM data rate was 270.83 kbps. The actual data rate that was achievable through this GSM standard was 270.83 kbps, whereas the maximum possible value of data rate is this value 69.86. So that means for GSM standard we only achieve around 40% of the theoretical limit for 30 dB SNR conditions. Similarly, we can solve the same problem for 30 dB SNR, which is for which the solution is available here, and for that case the maximum possible data rate comes out to be 1.99 megabits per second. So after discussing some of the basic concepts related to the digital modulation schemes, we now discuss the different digital modulation schemes that are used in mobile radio channels. Generally, we characterize modulation techniques into two major categories. One is called linear modulation technique and other is non-linear, that we will discuss later. So for linear modulation techniques, the amplitude of the transmitted signal varies linearly with modulating signal. So amplitude is actually linearly related to the modulating signal. We represent that expression with this expression here. This MT represents the modulating signal and e raised to power j2 pi fct is actually representing the carrier signal. And you can see that because of the complex nature here, we can represent this thing into two different parts. First one, this MR is representing the real part and MI is representing the imaginary part. This signal can be represented as sum of two components. You can take it as a cosine component and sine component. Sometimes we represent them as I and Q component. The cosine component is named as in phase component or I component, and the sine component is represented as quadrature component or Q component. These linear modulation techniques, they are typically have very good bandwidth efficiency, and this property of having a better bandwidth efficiency makes these linear modulation techniques attractive for wireless communication. But the problem with this linear modulation technique is that they should be transmitted with the linear RF amplifiers, and generally the linear RF amplifiers, they have relatively poor power efficiency. So if we try to increase the power using a non-linear amplifier, in that case these modulation techniques lose some spectral efficiency, as well as they cause adjacent channel interference, because these non-linear amplifiers, they generate some power in the side lobes as well. So eventually the overall performance gets degraded whenever we use non-linear amplifiers, and if we restrict ourselves to the linear amplifier, then we can only have a limited amount of power efficiency, which is very poor for wireless communications. So these linear techniques have certain advantage of having bandwidth efficiency, but they have a restriction that they can be used with a lower amount of power efficiency by virtue of using linear power amplifiers. The common examples of these linear modulation techniques are BPSK, DPSK, QPSK, offset QPSK, etc., and all similar techniques, they come under category of linear modulation techniques. So let us quickly discuss binary phase shift keying, BPSK, which is one of the example of linear modulation technique. For BPSK, the binary signal is represented by two different phases. So say for example, you can see that binary 1 is represented by a one phase and binary 0 is represented by another phase, and these two points, they have 180-degree phase transitions here from 1 to 0 and 0 to 1. You can see that we have a phase change of 180 degree. So BPSK signal is represented by two different phases, either 0. So 0 is represented by one phase and 1 is represented by another phase. Or we can think of the same thing as the amplitude reversal, because 180-degree phase change represents a reversal in amplitude sign. So we see a amplitude change from positive to negative when we have different symbols. Because binary phase shift keying, the information is encoded in the phases, so it is very important to properly determine phase at the receiver side. In that case, we need to transmit the carrier along with the transmitted signal as well, in order to properly synchronize the transmitter and receiver. This type of detection at the receiver side is named as synchronous or coherent detection, which is generally complex and costly receiver circuit. But the good thing for this case is that it has a very good BR performance even for low signal to noise ratios. So these schemes are this BPSK is having very good power efficiency. QPSK is actually QPSK or quadrature phase shift keying is actually an extended version of BPSK, where we use 4 symbols instead of 2, because for binary shift keying we are using only 2 symbols. For QPSK we use 4 symbols, and we use 4 different phases to represent those symbols. So say for example 00 bit makes one symbol and it is represented by phase 0. 01 bit it is represented by another phase pi by 2. 11 is another symbol which is represented by phase of pi, and 10 is another symbol which is represented by 3 pi by 2. So actually one symbol is represented by 2 bits here, and different symbols are represented by different number of phases. This is a constellation diagram or vector diagram to represent a QPSK system. You can see here we have different symbols, and these symbols are represented by different phases. So a phase 0 corresponds to the bit sequence of 00. Phase of 90 degree corresponds to the bit sequence of 01, and so on. So these points, they are represented by different phases. Similarly, if we combine 3 bits into to make a symbol, so it will become a 8 array system, and that 8 array system would be represented by 8 different phases as listed here. So we can use an 8 array system. For that purpose, the constellation diagram would look somewhat like this. There will be 8 different symbols which would be represented by 8 array PSK, 8 PSK system. A variant of QPSK is named as offset QPSK. Actually, the main thing about main difference between QPSK and offset QPSK is that in offset QPSK there is a offset between even and odd bits. So two bits, the 2 consecutive bits, they are having some offset, and that offset restricts the transition of phases to 90 degree. So in one whenever a new symbol comes in, the maximum possible transition is 90 degree. For example, if you look at this diagram, say for example if you are having this symbol, so for next symbol you can go to this one or this one or this one. So there are all these possibilities. For this one to this one you have a phase transition of 90 degree, but for this one to this one you have a phase transition of 180 degree. So any possible combination of phase transition is there when you have QPSK system. For offset QPSK, the maximum possible phase shift is 90 degree at a time. So if you have a symbol here, in that case it can go to this value or this value. There will be no transition from here to here. In next symbol there may be a transition from here to here or back to the original symbol, and so on. So maximum possible phase transition would be only 90 degrees in offset QPSK. So far we have discussed some of the linear modulation techniques which we use in wireless communication. We will be continuing this topic in our next lecture as well, inshallah. So we stop today's lecture here. Inshallah we will continue the same thing in the third lecture of this week. Thank you all.